Hello everybody, welcome also from my side to this year's Geodict user meeting. I'm going to present a fatigue damage prediction with Geodict, and the application that we are looking at are short fiber reinforced polymers. I'm going to start by giving a quick outline. I will first give you an idea of what fatigue in short fiber reinforced polymers is, what are the challenges that we are facing when trying to predict fatigue damage, what we see in experiments of what kind of degradation processes we are dealing with. And based on that knowledge, we are then going to present a material model for the matrix damage in order to model this kind of degradation or fatigue process. In a third step, we are going to discuss in detail how to implement this material model within Geodict using a UMAT. This discussion is actually not only limited to fatigue damage models, but might be also of interest for people who just want to integrate some general UMAT within Geodict. And in the last fourth step, I'm going to present the multi-scale simulations for short fiber reinforced polymers under fatigue loading, not only taking into account a single voxel structure that we computed in Geodict, but a whole set of fiber orientations. So let's start with short fiber reinforced polymers. Short fiber reinforced polymers are composite materials consisting of a matrix and fibers. These fibers have typical aspect ratios of 20 or 25, and they're steered into the matrix material and then extruded via an injection molding processes and injected into a component at some predefined points. This kind of process is very good for a high number of produced components. It can be optimized quite easily, and it's just rather easy to produce this kind of components. But what we get on the material side of view is a rather complex microstructure within the component developing due to this process. So if we inject this kind of matrix fiber mix into the component at one point, we will see that the fiber structure developing in the component might be rather complex. For example, on bar-like structures shown in purple here, we will have a lot of fibers pointing in one direction. We call this unidirectional. And on other points in the component, we have rather planar isotrope or even isotrope structures. So we need to understand how this fiber orientation influences the macroscopic behavior of components. If we now take a look on what fatigue does to this kind of components, we will find in the literature some experiments that show that over the number of cycles n, the material actually degrades in its elastic properties. So we will see that starting from an elastic property, for example, the Young's modulus E0, in the first stage, we get a rather pronounced degradation, taking not too much of the fatigue life of the specimen. Then enter a second stage where we have a moderate degradation over a long time. And in a third and final stage, we will see the failure of the specimen. What we are interested to model within this presentation is only stage 1 and stage 2 of the fatigue degradation. This is due to the fact that in these stages of degradation, the damage on a microscale level is not localized yet, and we can use from a mathematical point rather advantageous formulation and be sure that our multi-scale approach works properly. So to maybe sum up the challenges that we are facing when we try to predict the fatigue degradation of the reinforced material, I show here an overview of the fatigue degradation dependence on the fiber orientation or the fiber structure. It might depend on fiber orientations. So if we have a rather isotropic or a planar isotropic structure, will make a huge difference. Then it will also depend on fiber aspect ratios, so how large, how long these fibers are in comparison to their diameter, and on fiber volume contents, so how many fibers are steered into the matrix material, and possibly on many more, like for example, fiber length distributions, fiber orientations of higher order, and so forth and so on. So computational homogenization is actually kind of the only way to integrate all this kind of dependencies, or to understand all this kind of interdependencies, and to predict the reinforced material. Okay, so now that we know that homogenization is kind of the only way to understand all of these dependencies on the fiber structure, we start by defining the material models of our constituents. And the material model that we are choosing for the damage model is a continuum damage model. There are continuum damage models in the literature which are rather well established, and it's usually based on a non-convex potential as shown here. And non-convex also means that it's not well posed, so we need a gradient enhancement to obtain mesh independence for these kind of models. Also, with a gradient enhancement, we need a non-standard solver to solve a multi-field problem. The alternative approach that we are trying to follow here is rather new in literature. It's a convex elastic potential, which is damaged by the variable d, which is set in the denominator of the material. And the advantage is that it's well posed. It doesn't need for a gradient enhancement, and it's still not mesh dependent. So standard solvers are applicable, but there is no localization process in the damage field to be seen. So it's only suitable for this stage 1 and stage 2 degradation processes that I mentioned when we looked at experimental results for the fatigue degradation of short fiber reinforced polymers. So we use this compliance-based damage model to directly model the degradation in cycle scale. This means that we formulate the elastic potential based on the strain amplitude and directly obtain the stress-strain relationship for a stress amplitude from this elastic potential. And then the damage evolution law is formulated directly in logarithmic cycle scale. So the d scratch means that we evolve over the logarithmic cycle scale. If we do so, then the damage evolution under constant stress amplitude looks like shown on the left-hand side of the slide here. And if we reintroduce this into the stiffness degradation, we will see that we actually obtain exactly the stage 1 and stage 2 fatigue as we have seen in the experimental results at the beginning of this presentation. So what we do to use this kind of material model within GeoDict is that we add a material to the database in which we use a UMAT. We formulate the material model as you've seen on the previous slides, use a UMAT to define the resulting stress and damage evolution, and compile the function to a UMAT file. And then we can add this UMAT file to a predefined material in the database of GeoDict. We start by going to Settings and Edit Material Base. We then enter the material name and click Add. Choose Mechanical Properties in the tab General. Switch to Mechanical Properties and enter the material name. And then select UMAT as a material law type. Now you can read the UMAT that you just compiled to this material as shown on the picture, and set material parameters in the tab Material Parameters. In our case, we need 3 material parameters. You have to scroll to the bottom of the tab. It's a bit hidden. And then you can enter the number of material parameters that you want to define, and subsequently also define them. In the last step, you need to define the number of state variables that you want to have. In our case, it's the damage variable, so it's just 1, and the initial value is set to 0. Finally, you can click Save Database, and you will be able to access this material in the GeoDict computational settings. You can load your favorite microstructure and go to ElastoDict, Predict ElastoDict. Click Edit to set up the simulation, and then click on the material ID which you want to assign the new material to. You can choose the new database entry that we just added to the database and choose OK. Finally, the setup load, you have to set up the load case and click Run. You can finally visualize the damage field or any internal variable that you have defined to exist. So in our case, the damage field on the structure that you have computed. Now, returning from the more technical perspective that we have just discussed in how to implement a UMAT within GeoDict, I want to return to the discussion of the effective stiffness evolution in short fiber reinforced polymers. And the stiffness bodies, or the Young's modulus bodies of short fiber reinforced polymer structures are shown on this slide. And in case they are not isotropic, so if the fiber structure itself is not isotropic, then also the stiffness is not isotropic, as shown in the blue or the green case here. Also, the evolution of the stiffness is anisotropic. So starting from an anisotropic initial state, the evolution or the degradation in each of the directions of the Young's modulus also depends on the fiber structure and the load case. And you can see here the case of loading in X direction. The coordinate system is also shown on the left here. That for this case, the stiffness degradation shown here in a relative manner is anisotropic. So for example, for the planar isotropic case shown in blue here, EX does not evolve in the same manner as EZ does. In the previous discussion, we can understand how fatigue damage evolves on a fiber structure. But what we finally want to actually do as an engineer is to understand how the behavior of a whole component is under fatigue loading. And what is actually the problem when trying to simulate a whole component is that a fully coupled simulation. So fully coupled means that to every, for example, finite element that you have discretized on the macroscopic scale, fiber structure of the underlying microstructure is directly linked to the material law in this point, that these kind of simulations are not feasible with the computational means that we have to these days. To give you an idea how long it would take to simulate a structure with about 3 million elements, which is what we roughly get if we discretize the structure shown on the left-hand side. it would take about 200 years on 256 CPUs to compute. We developed a multi-scale model that is based on reduced order modeling and helps us to compute these kind of components in an efficient way. The surrogate model or the reduced order model is built on precomputations of a fixed set of fiber structures, which we subject to different load cases, and then extract their stress and damage modes that are typical for the solution fields obtained from these simulations. Then a method called non-uniform transformation field analysis, or short NTFA, enables us to derive macroscopic equations. This is basically a method built upon reduced order modeling. We can store the system matrices derived from the NTFA approach into a database, and finally, via a fiber orientation interpolation, associate the macroscopic elements to the material law stored in the database. And this enables us to computationally efficiently predict the macroscopic component. An idea how fast the speed up is, we conducted a component simulation on the shown component, and instead of roughly 200 years, it only took about 5 hours to compute with the reduced order model. To sum up my talk really quickly, under fatigue loading of short fiber reinforced polymers, we observe a matrix damage which leads to the degradation of the stiffness of the composite. And we model this kind of degradation or fatigue damage via a non-local damage model for the matrix material. And this is doable without gradient extension, so standard UMATs can be applied. We demonstrated the usage of standard UMATs within GeoDict, and we are able to study the local damage field and the stress redistribution due to the UMAT implementation of the damage model. Also, from a homogenized point of view, we are able to study the degradation of the stiffness of the composite. This kind of damage model is also applicable for multi-scale simulations. There is a database concept readily available, and with this kind of multi-scale approach, computations of engineering components becomes feasible.